Wow.
Okay, so we're looking at Cambridge Extension 2, Exercise 5C, Question 11. They give us two vectors, A and B, and they want us to find a vector that's perpendicular to both. Right? Well, we've written down some results that we know. We know that the modulus of A times the modulus of B times cos theta equals the dot product of A and B. Let's come up with let's call our perpendicular vector C. Now, the thing about a perpendicular vector, if I have a vector, just think in 2Ds. If I've got a vector and I ask to find a vector that's perpendicular to both, thank you, good sir. Thank you. If I ask to find a vector that's perpendicular to both, thank you. If I look for a vector that's perpendicular to both, that vector could be this vector, or this vector, or this vector, or even that vector, or that vector. So it could be a vector of any magnitude in either direction. Okay. Now, let's neaten that up a bit. If I have this vector here and I want a perpendicular vector, I can arbitrarily say that I want the horizontal component of that vector to be 1. Okay, and that means that depending on the angle between these two, between this vector and this vector, that's going to change what the vertical component of the vector is. So I'm going to arbitrarily assign a value of one of the components of my vector C, and I'm going to use that to help me solve my problem, because I'm going to end up with this. So if I look at A dot C, if they're perpendicular, then A dot C is 0. Well, this is what A dot C is. A minus B plus 2C is 0. Yep. And if B and C are perpendicular, then B dot C is 0. So I get 2A plus B minus 3C equals 0. My problem is I've got 2 equations and 3 variables. Yeah. Can't do it, right? Yeah. 2 equations need 2 variables, but nothing stops me from arbitrarily controlling the length of one of the components of vector C. Right? So I'm going to say let A equal 1. It's nice and simple. So I end up, equation 1 becomes 1 minus B plus 2C is 0, and equation 2 becomes 2 plus B minus 3C equals 0. I'll call that 1.1 and I'll call this 2.1. Well, now I've got 2 equations, 2 variables, no problem at all. So I'm going to add my equations to eliminate the variable B. So 1.1 plus 2.1 gives me 1 plus 1 is 3, minus B plus B is nothing, 2C plus negative 3C is minus C equals 0. Well, that means that C is 3, and just very simply substituting C equals 3 into, doesn't really matter, equation 1.1 gives us 1 minus B plus 6 equals 0. So 7 minus B equals 0. So in other words, B equals 7. So a perpendicular vector to A and B would be the vector C, which is A was 1, so it's going to be I, so 1I. B was 7, 7J, and C was 3. That's a perpendicular vector.
Okay. Yeah, and if you change any of the variables.
Yeah, that's right. I mean, I could have arbitrary. I mean, that's right. Well, I can lengthen a vector. Yeah. So I could multiply this vector by 3, or 2, or negative 4, or 5. It doesn't matter. So I can change its length, but that doesn't change the angle it has or the angle it makes with any of the other vectors. Test them out. What is the dot product of A and C? Not using the angular method. So I get 1 minus 7 plus 6 is 0. What about with B and C? 2 plus 7. What do we do? 9 minus 9 is 0. That's right.
Wow. Okay. Okay.
And even if you would multiply by a scale, let's say I had 2y plus 14j plus 6k.
Yeah.
Say, just to try the dot product, I had 2y plus 14j plus 6k.
14 minus 18, which is 0.
Which is 0, that's right. So multiplying it, so stretching it or
Oh, that's cool.
it is, isn't it?
Wow.
Very good.
Yeah, I couldn't imagine. I didn't visualize it properly in 3D because I was like, if you change one of the components, wouldn't that just change the whole angle?
Well, if you change one component, yes, it will.
Okay.
But when we multiply by the scalar, we're not changing one.
Yeah.
We're just changing the length.
Yeah,
that's right.
Yeah.
Okay?
That's way much